Hello and welcome to the talk Industrial Protocol Gateways Under Analysis. My name is Marco Balduzzi, I work for Tremaico Research, and this is a joint work between myself, Charles Rainer and Philip from Trent, as well as independent researcher Luca Bongiorni. So today we talk of protocol gateways, devices like this that have been in the market since many years now and were heavily used in smart manufacturing, and they play a very, very important role when it comes to the integration of IT and OT. This is because smart manufacturing plants, they are very complex. For example, they might have different networking layers. For example, there is an enterprise layer in the top where you have a business logic of a company, including the cloud and the data that are stored over the internet. Then in the middle you have a control network that run, for example, a server for controlling the production, and then down to the field network, which is the lower network, you have devices like PLCs as well as actuator, motor, and so on and so forth. All these networks have to communicate, and each network rely on different protocols, and there are a lot of different protocols that are very similar to each other, like for example Profinet, Ethercat, ANET, and so on and so forth. But you need something that can bridge this protocol together and make all of this actually interoperable, make all of this like talking to each other. That's where protocol gateways come in place, and they play a very important role. So as you can see here on the screen, this is an example of a actually, I have a gateway I have here in my hands. It's pretty much long, like 10 centimeters, so not big. There are different interfaces, and the gateway basically what it does, it translates different protocols, so it understands the semantic of the protocol, it parses the protocol, and it takes appropriate action based on the inbound traffic it receives. So it can connect an Ethernet interface to a wireless interface, an Ethernet interface to a serial, as well to the internet. A typical installation like this one you have on the screen. So you have like a network, a green network on the top of the screen that might run, for example, TCP/IP. This could be normally like a control network, no? So you can have like a control network controlling the network here on orange and red, which is the field network. And on the control network, you have an HMI, for example, which is a master node. So the node that take action, that, for example, configure a relay based on the temperature read from a PLC, and so on and so forth. Suppose you have a master node on the green network that has to talk to a slave node on the orange network. So what happens? You have, for example, a Modbus TCP node that in that case have to talk to a Modbus RTU node. So to be able to do that, you need a device like a protocol gateway that handle the translation between these two networks and can speak concurrently Modbus TCP and Modbus RTU. This is a typical installation, and this is very frequent when you have devices that run on legacy networks like serial, and you have to bridge this legacy network and to bring them in your IT environment. Note that often there is also an SES firewall, which is like a mechanism that prevent unauthorized command. It prevent, for example, an HMI to write registers that are not allowed to be written because are protected. So it might, for example, only allow read request. So as a result of these protocol gateways, they are a kind of teeny chip, and for many people just embedded piece of hardware, so they don't give much importance to these devices, which actually looks like, maybe performing only secondary tasks. They are not like industrial robots that build things, so you don't see them doing something concretely, but that's really not true. They play an important role, especially when it comes to the network. No? They are core to the industrial network. If something goes wrong with these devices, it's not bad, right? And on top of that, they actually run a fully fledged system. So they might have many of them like a real-time operating system. So there are a lot of functionalities. So they are not so simple, if you want. No. So as a result of this is that these devices tend to be often overlooked or not indexed at all, like in the asset of a company, and the consequence of this is that they might not go into properly patching, they might not be monitored, they might be misconfigured, and so on and so forth. So that's why we did this research. So our goal is really to understand The problem when it comes to the translation capabilities of these devices, how this problem may affect, like in a real world, for example, a factory or a production. And we do it in a different way when compared to the past. Like if you take this research presented in 2018 by Thomas, I show that this device might have significant vulnerabilities. But we are not interested as much in compromising the device, but rather, as I said, looking at the translation. So now understanding how a protocol is translated into another protocol, and doing this analysis on the technological layers. We are not much interested in finger pointing against specific vendors, but rather understanding how different vendors implement this translation and what could go wrong. We also decide to focus on Modbus because it is a widely used and popular protocol, and it extensively covers both the control network and the field network. So overall, we consider five vendors with 5 products, and they are pretty much similar to each other in the sense they all have like at least Ethernet and serial interfaces, speak Modbus, and they are widely distributed worldwide. And the two main, there are just 2 main categories of these 2 products, which is important to point out here. Some of them are real-time gateways, in the sense that they do a one-to-one in translation. That means that each incoming packet is forwarded to the outbound interface one-to-one. So one incoming packet, one outbound packet. While data station make use of an asynchronous approach. For example, they do not wait for an incoming read to pull data out from a slave. So they do it for performance reason, which is okay, but this way of working asynchronously and as well relying on an internal mapping table called IO mapping table complicate things. So we'll see later in the presentation how this sort of routing table complicate things. So let's look at how we approach our research. So we voluntarily decide to go through via a black box approach, in which we have a researcher that leverage a fuzzer to generate appropriate test cases for the gateway. And these test cases might, for example, as well, crash gateway or create problem to the gateway. So we have also a loop system for monitoring problems, which what we call crash monitoring, and is run by the fuzzer itself. What the gateway does when we receive the traffic, it actually translates the traffic and it translates down to a simulator. So simulator play a very important role, especially for data station that need to know what's connected on the back to operate properly. Then we have a sniffer that collect outbound traffic from the gateway and bring this traffic down to the analyzer together with traffic coming from the fuzzer. And the analyzer take decisions based on the fact that the inbound and outbound traffic is the same, is not the same, has changed, there is not bound traffic compared to inbound traffic, and so on and so forth. So let me now show you by means of some screenshots related to the simulator how the Modbus protocol, what the Modbus protocol is, and how a protocol gateway operates with respect to this protocol. So suppose you have 2 simulators, like this one you have a screen. One is on the left is a master, one is a slave. So the Modbus master is connected via TCP, you can see the address here. The Modbus slave is connected to the serial port of the protocol gateway, you can see it here. We made use of a simulator because it works pretty well. It's freely available online, so thanks to developer of this application. We changed a few things around, but overall we use the application as it is. And it worked pretty well for us. So we were able to simulate both master node, both a slave node, both on serial, both on TCP, so very good. So when it comes to the master, let's say for example the master generate a read request starting from address 0 for 5 coils. So this request get forwarded to the gateway. What the gateway does, translate the request for the slave. The slave replies by the value of these 5 coils down to the master. Very simple. What happened on the back end is that the master generated a packet like this. So you have a header, which is it's called Modbus TCP header in yellow. And the payload. The payload consists of a command, in this case a function code 1, which means read coil and read 5 coils. So what the gateway does when you receive this packet, it extract the payload, take the payload, compute the checksum, and add the checksum as a 2 bytes trailer to the payload. Then the Modbus, a new packet called Modbus RTU, is sent to the slave. The slave reply with a value, in this case X15. This payload get reprocessed by the protocol gateway in the back, we generate the header and send back to the master. So this is how it works. On top of that, we have a fuzzer, as I said. So we use a generation-based fuzzer that works pretty well when you have protocol with known specification like Modbus. In our case, we rely on a code based on BuFuzz for Modbus that we modify to our needs. We manage, for example, to create things like this. So this is a snippet showing how you can easily fuzz a write single coil command. So without going detail here, since we don't have as much time, we can fuzz different field. For each field, we can specify the byte ordering, how you want to fuzz it, if you want to, for example, cover all the other space or not, the order, if you want to add, for example, a recursive field or a trailer at the end, for example, to generate very large packets that potentially might potentially trigger, for example, a denial of service condition. We can also do instrumentation, so we can monitor if a device we are testing might crash, for example. We can do it via connect or ARP request, whatever. So whatever we want. And on top of that, of course, I said we had to sniff, so we had to capture inbound and outbound traffic. For the inbound, for TCP, we use like Wareshare. Like for serial, we use IONinja, which works pretty well. At the time when these two sniffers create their own logs, we extract from the logs the packets we are interested to. We normalize the data, and we do it in a way that the analyzer then can easily correlate inbound and outbound traffic. The correlation is made via timestamp when it comes to real-time gateways, because there is a one-to-one matching between input and output, while for data station we made use of nonce, like random value that we insert, that have been inserted by the fuzzer. So we ask the fuzzer to insert these nonce in the inbound data, so that we can then easily map outbound with inbound. So here, for example, on the right, there is a session where you can see a real-time session. You can see TCP RTU, TCP RTU, TCP RTU. So this is a classic example of correct, actually, it's even correct forwarding of traffic between TCP and RTU. This is an example of setup where you have a gateway down here that translate TCP into RTU. On the RTU, we have a tap that we use to collect data and send it to the sniffer. On the TCP, we use a monitoring port of the Netgear to collect data as well. Then we have a second Arduino up here on the left corner that simulate the every Modbus master or slave and also implement the fuzzing capabilities. And all of this, in the center of all of this, there is this network power strip that we use to reboot the device when there are problems. Let's go for a finding here. So let's start with the resource exhaustion, because it's a very common problem. Like we found that all the devices we test are affected to a certain extension to this resource exhaustion. What happened here is that either the device hang at the TCP IP stack, so it's not reachable by even single command like ping, or it hang on the translation process, so it's still up and running but does not translate. Of course, this is very severe because even if you block something like this, of course, production is blocked, right? So it's really a problem, and it's very easy to cause such a resource exhaustion thing. Like here you have, for example, a fuzzer that generate a test every second, as you can see down here, for a total of 20 kilobits per second. So not much, but even at this low bandwidth, the device that you can see here has been detected to be crashed, is not reachable anymore, and the power socket jump in and basically reboot the device, which got reboot. And you can see here the new uptime is just 5 seconds, and as you can see, you have a fuzzing restart. So this is the way in which we process, basically. We go, we fuzz, the device reboot, we continue to fuzz, and so on and so forth, until we find something like this. So this is a targeted denial of service occurring against Red Lion in case we are going to read addresses that have a value of 0. So which is legitimate, 0 is okay, but since this one is a data station, as we will see later in the talk, 0 here is used as an address in the internal mapping table. So In this case, the device has really problem with addressing the mapping table at address 0. So let me show you here an example of this. So here you have basically the attacker that generates such a packet for this IP address, which is the device. The packet is sent, as you can see here. As soon as it's sent, the device turn off and reboot. The reboot takes about 20 seconds to run. That's why you don't see any more logs coming down here, but when the reboot is finished, the device will send a notification that there was a connection false. Again, the attacker generates a second packet here. The device, as you can see, will crash again. All the LEDs go down. So it's very, very easy to trigger such a reboot by remotely send just a single packet. So imagine you have an attacker like in the control network, one packet, you go down basically. So let's now jump into the protocol translation bypass problems, which are actually the core of our research. So we start by evaluating how well our devices do with respect to dropping malformed packets. So if there is any good filtering mechanism in place, and it turned out that one of our devices actually didn't filter any single of our malformed packet. And this one we see here on screen is one of those packets. Is a read input register command where we are asking to the slave to give us basically 70 registers starting from this address here you see on the screen. So the payload here is 6 bytes long, as you can count them, but the field here in the TCP header specify a message length of a payload of 11. So there is an inconsistency between what has been said in the header and the real content of the payload. As a result of that, the device does not properly translate these packets. Actually, it does not translate at all. It just takes the packet and forward the packet as it is. So as a result, you will have like a packet that has been it's basically a Modbus TCP packet that will be propagated on the serial interface. And this is very severe because the semantic of the two protocols like Modbus TCP and Modbus RTU are different. What does it mean? It means that such a packet that in Modbus TCP read as a read input register because its function code is 4, in Modbus RTU it reads as a write multiple call command. So what does it mean? It means that if you have an attacker that has, for example, compromised an historian like a database on your control network, he can easily send a read request, which is a super legitimate request that every ICS firewall will allow to trigger actually a write down here in the production network. So he might, for example, be able to turn off a relay or turn off a thermometer and cause a damage right to the production. So let me show an example of what I said here. So let me kill this one. Let me go for this other demo we have down here. And I'm going to show you, this is our gateway, which is this Neo 50 that is running. The gateway is correctly translating Modbus from Ethernet to serial and is listening on port 502 for incoming Modbus TCP request. So what you will see here, you will see this is a sniffer on Modbus TCP that we run on backend. Then we run a sniffer on Modbus RTU on the backend as well. Then we'll have an attacker that will use a tool to generate appropriate traffic. In that case, it will specify the payload that will have as function code 4 and the different fields as we show on the screen, right? So 70 register from that address. Here on the small screen, you have open PLC. So this is like an example of a real running PLC server where you have relay and motors which are on. You can see that correctly is reporting the temperature to the PLC as well as some other information by a tachometer. So what the attacker will do by a single read command, it will actually trigger a write and it will disable everything except the motor, making basically the system going in panic because the system will continue basically producing, the motor will continue running, but there is no temperature reporting back. So it might be super severe, this stuff. And I'm going to show you that on the push command sent from the attacker, there is the packet that has been generated by the tool. As well, I'm going to show you that on the serial side, the packet is exactly the same, confirming that there is no translation but a simple forwarding made by the gateway. Of course, this is just an example, but it's super severe in the sense that this attack and this vulnerability related to the translation problem of the device can be used to do anything. So the attacker, it's up to the attacker to be able to design his own preferred attack. So it's a nightmare. Let's see something which pretty much is pretty the same, like the same flavor attack for data station. So as I said, data station are a bit more complex devices because they don't operate in real time, but they have multiple routines that work asynchronously. For example, normally you have one routine that parts for the incoming traffic and set appropriate value in the mapping table based on the traffic it received. And then you have a second routine that scans for the mapping table, and if there are actually changes in the mapping table, it generates the appropriate request for a slave connected to the back. So in this example, we have two commands being configured in the mapping table, one for enabling disabling a coil and one for setting a critical temperature. And these commands are mapped down, as you can see here, to internal address 0 for the first command and internal address 2 and 3 for the second command. Second command requires 2 bytes because it's a write register. So to write, to set a temperature, which is an integer value, you need 2 bytes. No? It's a 2-byte space. So what happened here is that at the time when there is a change, for example, in let's say bit number 5, which is on the first byte, what will do the data station will be is to trigger a set software 1, no? So to trigger the first command. So there is a weird fact here, the fact that the address of inbound message is used as an index in the mapping table. What does it mean? It means, going back here to the example, suppose this device receive I don't know, like write coil 5. What it will do, it will generate another write coil because this command here corresponds to function code 5, so it will generate another write coil, okay? So this is pretty much weird anyhow, because if I send the write coil 5, I would expect, that 5 means basically the address on the slave, not the address on the mapping table. But, okay, this has been designed, let's take it as it is. The problem is the out-of-bound vulnerability we have discovered, in which the attacker can do a write coil N or X in this case, like see here, where X is anywhere in the table, so it can overflow the table. It can go and write in address of the table that are not mapped. As well, there is no check for function code. That means that an attacker will be able, for example, to trigger a write register within a write coil, and vice versa, or even worse, it could use a write multiple coils command to overflow the table. At that point, basically, all n write coil or n potential write register will be triggered on the slave. For example, causing an amplification attack. So let's give you an example about this. Let's assume an attacker wants to change a protected parameter, like a critical threshold, we say in the past, which has like default value of 200. So this change is not allowed because write requests are blocked, and only write coil command are allowed by a firewall. But we'll show you in this demo how it's possible to do that by abusing this vulnerability. So let me go here and start showing you Mox attack. Now it's named Mox camera 1. Our setup. So in our setup, we have a vulnerable gateway, which is this gentleman here, which is power on, of course, connect with 2 interfaces. The either interface go to the fuzzer, or in our case, the attacker. The serial interface with this silver cable go down to an Arduino, which implement this open PLC logic. So this PLC is connecting to a board that contains different LEDs for relay and motors, as well as a siren. The siren gets automatically triggered when the temperature read by the Arduino, in this case, it goes over, so above, the threshold, which is by default 200. Now I'm showing you how things are. So in a normal situation, the engineer uses this write register command and write register packet, which has function code 6 to change the temperature. So, for example, 3000 for 300 because you have to convert an integer into a float, and we are one off. But that's okay. So suppose that's the right way to change this value. And normally this function code 6 is, for example, blocked by an SES firewall, no? To prevent unauthorized change. But an attacker basically would abuse of a protocol translation problem, and we use the write coil to flip a single bit in a way to change the temperature. For example, by flipping bit 22, we can raise the critical threshold to 1800. So such a high value would probably not be hit never. So at that point, basically, if there is like a process, you might melt the process. I mean, you might really damage the production. And even worse, since this is an integer value, an attacker can do an integer overflow. He can flip the most significant bit, which in this case is the at address 23, and it will basically set critical threshold temperature at a negative value, and the alarm will be raised consequently. I can show you down here in the camera. So this is exactly what I said. You have an attacker that by means of a single write coil command, flip a bit, bring the critical threshold at a negative temperature. At that point, the alarm is actually triggered on the PLC. Of course, this is all possible, and this is summarized here. So this is the correct way of doing it by using a write register, by changing address 1. This is actually the way to abuse of such problem with the protocol translation in this data station, to flip one bit and to create the things I show you on the screen, on the video. Of course, all of this is possible. Of course, if attacker know more about what sits on the back of a protocol gateway, and know more about the mapping table, it can perform more targeted attack instead of doing a blind attack. So we have discovered different techniques to leak the IO mapping table, and all these are vulnerabilities that we reported to the vendor. So the first one is by token credential reuse. So the problem here lies in the fact that the password is encrypted with a nonce that is not correctly initialized. So an attacker can reuse the same nonce over and over. So as you can see here, this is part of a firmware that we reverse engineer to discover the problem. So rand does not have an initialization vector. So v11 is used in this get challenge function. And as a result of that, every time this SDC underscore function is called, this challenge gets initialized always with the same value. And this is the case after reboot, reconfigure, update. So in this case, an attacker can reuse the same token, and which will give them full access to the device, not only the mapping table. Another way is to decrypt the configuration that is exchanged over network. So the attacker can dump the configuration, and the configuration itself is encrypted but contains the key to decrypt it, so which is super lame, no? I mean, and the configuration is IES, but the key is included, so the attacker can simply use the library provide like included in the Moxa firmware, for example, this underscore decrypt confidence conf1 AES, and as we can show here, they can use QEMU to emulate the library, run it against the encrypted content that has been stolen by network, and decrypt all the configuration, including the mapping table. The fourth way of doing it is the authenticated privilege escalation, a vulnerability that we have found in the web console, in which an unprivileged user, like a read-only, can abuse the common injection vulnerability in the ping destination form, as you can see here, to run a telnet daemon as a root. So I don't really understand why ping needs root to be run, but that's the thing. So at that point, you can, with this command here, you can basically inject like a telnet at the point you connect back, and you are root. The other option is to use a memory leakage vulnerability that we found in another of our products. Here we have an example of attack payload where you specify 4 registers to be read and the number of bytes set to 0, which doesn't make any sense. So in this case, what happened is that the device leak part of its memory to the slave in form of registers that are set to the slave and then that are then also read back. This is because the data station it keeps only synced its internal cache with the value of a register on the slave. So at that point, an attacker can read all the data back from the data station. As we can see here on screen of the screenshot, an attacker can, for example, leak part of this register 40563, which is exactly this one in the mapping table. We are still investigating this case, but it looks like that the amount of data you can leak is proportional to the number of registers to write field specified in the attack value with a cap of 16 bytes per request, and the address that you're going to leak is predictable because it's a function of a starting address field specified in the attack packet. We also found a bunch of other translation problems that I would like to discuss with you, but given the fact that due to this coronavirus problem, our talk has been reduced from 50 minutes down to pretty much 35 because there are questions upcoming. I'm going to mention briefly here, but there are way more in the paper that we are going to publish together with the presentation. So there are a lot of problems when it comes to the translation from your network, industrial network to the cloud. For example, the fact that there is a lack of encryption or the fact that the encryption is broken, so an attacker can steal confidential data, like data coming from sensors. There is a lack of sanitization, so an attacker is able to inject, for example, SQL injection command into the communication between the protocol gateway and a database running in the cloud and exploiting a vulnerability, a SQL injection vulnerability in the cloud. There is broken authentication and many others. There are still problems with availability. For example, the fact that someone can cause a denial of service attack by using a single packet like a single magic packet that would change the IP address of the device. There are problems with different implementation of the specifications and so on and so forth. So let me wrap up by saying that this device, even if they are small, tiny, and they are not as visible as an industrial robot, for example, they play a very important role in a modern smart manufacturing network, and they are core to the communication. So be sure to correctly configure them and manage them. Include them in your asset list, and really take care of a small device, because even if they are smaller, they might create big problems if something goes wrong, as we show here in our presentation. Then do not rely on a single point of failure. Like, you might say, okay, I buy an ICS firewall, I'm done. Well, not really, because the vulnerability we have shown you on the protocol translation, they are all vulnerabilities that allow an attacker to create a legitimate packet that would go through an ICS firewall, but would be converted into something else chosen by the attacker, and potentially very badly. That would, for example, disable a motor, change a certain configuration, change the value of the temperature threshold, whatever. So really, don't rely on a single point of control, but implement other heuristics like monitoring traffic on the serial, or include intrusion detection system, and so on and so forth. And lastly, try to consider security as an important aspect in the product selection. So I know that when it comes to embedded devices, security is not always there, but try to go for those vendors that provide at least some security features, because these devices need to be protected as well, especially because they really contain a lot of vulnerabilities and a lot of problems. These are only some of the problems that we reported to ZDI, but there are way more of this, but we have decided to not report yet, and we are still investigating and so on. But some of these problems have been fixed, some are waiting to be fixed, some won't be fixed, unfortunately, because we had really difficulties in talking to the appropriate parties. But we do our best. So the research we do is public. We want to raise awareness in this field, but we think need awareness. That's why we have done this research. Again, all the details will be disclosed in the paper that will be published at the time you see this presentation, and you can reference it through our social networking websites. And if you have any question, either reach me out via Twitter or feel free to ask me a live question. Thanks again for being with me, and have a nice day. Bye-bye. Hello, here is Marco from Italy. As you can see, it's pretty dark outside, out here where I am now. Yeah, thanks for listening. I hope you enjoy the talk. It was kind of a rush to make it into 45 minutes. But what I want to say is, yeah, today I sent basically to Black Hat Crew the paper, which is something like over 50 pages. So there is really a lot of material in the paper. You might want to check it out. And as well an extended version of a presentation where we included like problems when it comes to MQTT, for example, the cloud support, as well as a longer introduction of further works and everything related to how we test basically these devices. So I guess I replied already to many of the questions you guys had. Let me just go over here to see if there is something coming up here. Yeah, okay, someone is commenting saying, okay, to not expose the device over the internet. Okay, that's, obvious, but the problem is that these devices are often exposed to the control network. So it's not the internet, it's part of your basically enterprise. And if any of the machines in the control network are compromised, then at that point, basically you can attack your production network via the protocol gateway, and it's very difficult to debug such attacks because these embedded devices are very difficult to debug. They often don't have logs, and then the device does not basically show any problem. So the device basically make a mistake in the translation and bring the mistake down to the PLC, and so it's very hard to debug such things. That's also one other issue. Oh yeah, man, there is too many things here. How do you see traditional ICS protocol change in the future, especially in terms of authentication, encryption, etc.? Yeah, that's a good question. In the past, we did a similar work where we look at AES, which is like a protocol using maritime security, and that was also a protocol that has no encryption and no such things. But in the future, I guess ICS protocol will be more robust. But again, here the problem is not of Modbus. So Modbus is okay. It's the problem of how this ICS protocol is implemented in the device. So so you take like a protocol, even if the protocol is safe, but you implement it in a wrong way, like you do it in a router. No, you cannot say that TCP/IP is is a wrong protocol, right? I mean, but if your router is implement in a bad way, basically the translation, the TCP/IP translation, then you might have problems. So it's really a problem of the gateways, not rather of the protocol. But yeah, I agree with you that in general, the ICS protocols should improve in the future. Someone is asking, what do you want to couple with ICS firewall? Yeah, I mean, the idea would be that you monitor not only the TCP/IP side, like the control network, but also like the serial side. The problem, I mean, I'm not really an OT engineer or an OT expert, but my understanding is that from the serial side, there are not many, or actually there are no products doing like IPS or firewalling on serial. So at that point, you have to implement your own basically monitoring system. So you, for example, you can use a tap to capture data on serial. At that point, you can monitor, if what comes out of the serial makes sense or not. Yeah, so I have 1 more minute here. Yeah, there is not much, but in any case, I would say you have my contacts and also the contacts of the researcher that work with me in this research. So we are a group of people. They are all listed as well in the abstract of the talk as well in the paper. So you may wanna let us know in case you have further questions. So thanks a lot. Enjoying Black Hat, even if it's virtual, and have fun. Bye bye.